This is a nice paper by Tim Palmer, a physicist and a climate scientist from Europe. Now he's at Oxford. Bjorn Stevens is in Max Planck in Germany, I think Hamburg. Brilliant scientists who are physical climate scientists, and they raise some good issues in their papers. This one in the Proceedings of the National Academies of Sciences of the US is a nice paper that is titled "The Scientific Challenge of Understanding and Estimating Climate Change." And the tagline itself is quite powerful. Given the slow unfolding of what may become catastrophic changes to Earth's climate, many are understandably distraught by failures of public policy to raise to the magnitude of the challenge. So, as I said, there is no doubt that climate change is happening, and it has the potential to wreak havoc beyond what is already seen across the world. 2020 is tied for with 2016 for the warmest global warming record in instrumental period. Few in the science community would think to question the scientific response to the unfolding changes. However, is the science community continuing to do its part to the best of its ability? This is something we have to be reflexive of, reflect on and contemplate about. In the domains where we can have the greatest influence, is the scientific community articulating a vision commensurate with the challenges posed by climate change? We think not. Okay, that's coming from very credible people. This was raised before in another chapter. We are looking at projections for RCP 2.6. 2.6 watts per meter squared imbalance, the most benign pathway we can hope for staying under 2 degrees with a 66% probability. RCP 8.5, which is essentially the business as usual pathway, and it's looking at temperature changes and precipitation and sea level changes in the decades of 2081 to 2100 with the baseline of 1986 to 2005. And the main point again is that when you look at the places where the signal that is being projected is so in this here, for example, stippling dots in A and B indicate regions where the projected change is large compared to natural internal variability, and where 90% of the models agree on the sign of change. So why is it important to consider the internal variability? Because whenever you want to detect a trend, you have the signal has to be above the internal variability. Let's say year-to-year variability in winter snowfall or temperatures are 50 degrees, and you are trying to project a change in the order of a degree or two. You have to be very robust in claiming statistical significance of this change. So consensus among models is always a good thing, but immediately it points out in the precipitation projections that the projected change is less than 1 standard deviation of natural variability in the 20-year means, which means the confidence and the agreement between the models is not as high when it comes to precipitation projections. We have said already that precipitation projections are always a difficult issue, and this is a problem, right? Because models have difficulties in simulating precipitation. They are often parameterized, which means they are not driven from first principles or equations. There are empirical relations put in. So this we have to be very careful about. And change in sea level, again, the point is that the adaptation decisions of sea level have to be at very local level. Mumbai versus Chennai or Kochi. So it has to be very local, and models are not yet there in terms of providing this level of local information. So the Tim Palmer and Bjorn Stevens provide a box of on reliable global climate models, why they are needed for societal applications and advancement of science, of course for decision making, for extended predictions. So we should distinguish between predictions and projections here, because projections are out into, let's say, multiple decades, where they are not initialized predictions like for weather and climate. So this idea of multi-year predictions or societally relevant timescales, let's say out to a decade, are really done differently, and they are considered more valuable. And as we saw before in another chapter, we have to see where that predictability comes from. What is in the system that has memory for a decade that we can exploit? For example, for El Nino, it's the heat content of the ocean and the slow interactions between the atmosphere and the ocean that provide us the ability to predict the evolution trajectory. What are the possible predictabilities in the Earth system at decadal timescale? That's critical. Observations, of course, and theories. Theory is vital in making predictions about the future. So we must have robustly simulated changes from models that are more directly expressing the physical laws, and they should come with robust explanations. Okay, and they provide a way forward, a new approach to global climate modeling, and they suggest a new approach to climate modeling. Approach should aim to reduce climate models' dependence on subgrid parameterizations where possible. So this is the precipitation simulation problem that I mentioned, and account for their uncertainty where they cannot avoid parameterizations at all. Okay, like maybe land ice, maybe vegetation, biophysical, biogeochemical interactions, and processes that are critical but not represented in terms of first principles. To be successful, this approach must master and motivate technological innovations, particularly in computing, because with high resolutions, the computing demand goes up exponentially. And these should be given a sense of purpose commensurate with the task at hand. So there is, of course, a critical need for simulating and predicting and projecting the future just for educational purposes, intellectual curiosity, and knowing what the system is capable of in our toy representation of the Earth system in terms of models. But when you try to put them into decision-making stream, then there has to be reliability and robustness that can actually come with uncertainty metrics and so on.